right, does it work? Yes, okay. Welcome. Thank you all for joining. So today I'm going to be talking about the impact of micro-optimizations on large-scale applications. Is the microphone okay? Can, or do I have to get closer? Okay, just going to wait for some feedback. Okay, I guess I will just assume it's fine. So first, a little bit about me. My name is Damien. I work as a software engineer at Meta. I've been, or more specifically at WhatsApp, so I've been doing software engineering for a very long time, way too much time, probably over 15 years at this point. I worked on a bunch of different tech stacks. I started off with PHP back then. That was fun. Then I moved to things like React. I did like some data engineering, data analysis as well. And then at some point I moved to mobile. And right now in my current position, I do mostly mobile, but still a bit of everything else. Yeah, so just a little bit about me. A bit about the presentation. So first, we're going to look into what are optimizations, and then we're going to look at what are micro-optimizations, just to set a bit the terminology. Then we will look into resource optimizations specifically, and after that, we're going to look into the benefits of micro-optimizations and how to measure them. Okay. After that, I hear a bit of feedback. Is it just me or is it? Okay. Maybe I'm too close. I don't know. Can you still hear me fine? Okay. So after that, we will look at a couple of case studies of large-scale applications and how micro-optimizations helped. So these will be a bit kind of like censored, but not really, because I won't be able to show like any direct data or any direct like impact on anything. But it's going to be like around like how they work, how they helped, and what are kind of like the expectations. And after that, we're going to look at some best practices. So to get started, the big question, what are optimizations? Optimizations are techniques used to improve performance, efficiency, and reliability of applications. It's not limited to mobile applications, but I work in mobile, so I'm mostly going to be talking about mobile, specifically Android. In the context of mobile apps, this can mean something like minimizing the usage of system resources while still maintaining or improving the user experience. If we look at resources, the first thing we have to keep in mind is that mobile devices are very constrained devices. And building mobile apps is quite complex. It can be a bit simple sometimes, but usually it gets quite complex very fast. So since these apps work on the constrained systems, if we look at a phone, they are still quite tiny, right? Like they kind of grew again into this whole phablet thing, but still they are quite small and they have a lot of computational power at this point. But with that, our apps are also getting more demanding and our users want just nicer apps. They want to see higher resolution, they want higher frame rates, they want more connectivity, more networking opportunities, and more sensors. So we kind of get more, but we also need to deliver more. So to accommodate for that, we have a couple of ways, right? So we would only request data that is required to render the information, right, that is currently needed. So we can keep data in local caches or in databases. We can downscale resources to reduce memory footprints, so we wouldn't download, let's say, like a huge bitmap directly. We would just download like a scaled down version of that. And we can also optimize computations and choose efficient algorithms that fit into our use case. And lastly, or one of the other examples is we can defer computations. So if we think about the whole data processing pipeline, most of the time there are things we don't really need to do right now in this moment. So we can focus on the urgent work, the latency sensitive work, and defer the work that we don't need right now, right? Because usually the user just wants to get stuff rendered on the screen, but doesn't care if everything in the background happens right now or in, let's say, 200 milliseconds. So the purpose of optimizations is to make apps more performant, reliable, and efficient. And there's some quotes, some statistics. If we think about ANRs, so app not responding, those usually happen if the main thread is blocked. So we are doing too much on the main thread and the UI can't render frames, so it can't update the UI. There's a statistic that says like 60% of the one-star reviews on the Play Store mention app crashes or freezes. And a lot of those, okay. And a lot of those come from ANRs, for example, usually. Then if we look at the UX, if we are loading too much data or we have an inefficient database or a storage solution, this can also lead directly to a reduction in, for example, conversions, right? So 1 second delay to display something can lead directly to a reduction. If you're about to shop something, if you're in an online shop, you want to see stuff fast, you don't want to wait like 5-6 seconds until the page renders. In that case, quite a lot of us would probably already close the page and go to a competitor. And then if we think about apps like just about the Play Store, for example, there's millions and millions of applications, so there's a lot of competition. And if the application we're working on doesn't really work well, or it has like flaws in the core user path, then it's very likely that the users will just choose a competitor instead that does the same thing, but in a seamless and smooth experience. So if we take a look at different types of optimizations, we'll take a look at micro-optimizations in a bit. I just want to get into the whole topic first. So let's figure out what macro-optimizations are, right? They could be, for example, high-level decisions about the design or the architecture and functionality of the application or the code base. That could be, for example, choosing the right data structures, the right algorithms, or the right data flow in your application. It could be an efficient database scheme, or it could be caching mechanisms, for example. These would be generally larger decisions that impact the global data structure, the global flow, the global data model. In comparison, micro-optimizations are more small scale, a lot more small scale. So these would focus on specific parts of the code or the system that we want to optimize. This could be, and just examples, it could be using bitwise operations instead of arithmetic operations. It could be minimizing the object allocations to reduce memory pressure and to have less garbage collections. It could be optimizing the graphics rendering, for example, what I mentioned earlier with the downscaled images, or if you're drawing components by yourself, that could be optimized. So why do these micro-optimizations matter? The macro-optimizations will provide the foundation for a performant app. But then these micro-optimizations can have significant impact when they are combined with macro-optimizations and applied consistently throughout the code base. So this is important, especially in scenarios where every millisecond counts. So you have, for example, real-time processing, or the battery life is crucial, or you have resources that are severely limited, even more than on most of the phones we have. If we think about low-end hardware, for example, in emerging markets, that is where these kind of things become more important. But the micro-optimizations also come with a few challenges. Usually it can be quite difficult to measure the impact of small improvements, because it's going to be easier just to measure like changes if you make big changes, right? But the micro ones, it's like very tiny changes usually, so they may not be noticeable in isolation. It can also be hard to test them locally, for example on an emulator, because there's just too many variables at play. Usually you would be connected to Wi-Fi, so you would have to play around and kind of reduce the network conditions for your test environment. And the benefits may also appear in completely different parts of the application than you actually intended. For example, if you lower the memory pressure, this would lead to less out-of-memory errors, but this can also manifest in other parts of the code, right? So if you just look at a specific area, it might behave the same, but then suddenly you realize there are benefits all across the code base. Because you go through a flow, in the middle of the flow, you're not allocating as much memory anymore, and then 5 steps further, there's no out-of-memory anymore, or less. Probably a less, not no. And these micro-optimizations also come with maintenance overhead, usually. So heavily optimized code is usually more complex and harder to understand. It can be challenging to maintain and debug this code, because if you look at the example I mentioned of moving from arithmetic to binary operators, that increases complexity to read for sure. I think most of us prefer reading arithmetic operators than play around with binary all the time. But optimizing the code doesn't mean that it needs to be short and unreadable. In the end, we have to keep in mind that the compiler is smart. It's also very heavily optimized. So it will kind of do a lot of those optimizations for us as well if we just stick to, let's say, the best practices. So while these micro optimizations can be challenging, there are also a lot of benefits. There's, for example, the cumulative impact. That is kind of what I mentioned earlier, right? If you spread them out over the code base, if you improve like small areas of the code base continuously, you're going to notice that, or at least the users are going to notice that. Depends a lot on your user base, but people will notice. Then there will be reduced latency, since the micro optimizations would be applied to the critical code path. So the areas that your users go through a lot, and that will just reduce latency overall, because you're making them ideally faster, the path, right? And then the better battery life, that's going to lead to minimizing we are going to minimize power consumption, because if we, for example, use less resources, the system needs to do less as well. And there's a lot more benefits of these micro optimizations. So if we look at large-scale applications, this picture shifts a little bit. So if we imagine that the application we're working on is used by billions of people all around the world, then micro optimizations can not just improve the user experience, but they can also enable the users to actually use your application. If you think about older devices, limited resources, then this can expand our reach in certain areas. So it can increase adoption in, for example, emerging markets, where the phones are, people are not using like the latest phones, right? So people are using phones with more constrained systems, and this is where the micro optimizations will shine. But to actually prove that our optimizations have an impact, we will need to be able to measure them. So there's a couple of things we can look at to measure them. There's just plain old load time reductions. This could lead to an increase in user engagement and retention. There's battery life extension that can actually translate to more DAUs and improved satisfaction, because I guess nobody likes it when an app drains the whole battery. And there's also, for example, data savings that can lead to cost savings, both for the end user and for the company themselves. That leads to improved performance, faster rendering, because you're downloading less data, and more usage of the core features for users, for example, that are on a limited data plan. So a couple of common metrics that we can use would be, like I mentioned, right, the execution time, CPU usage, memory allocation, and power consumption. Those would be like common metrics for micro optimizations. And let's go into an example. So if you're measuring, for example, the execution time, to collect the delta, the time difference delta, we will need to record the start and end timestamps. We can do that on test devices, or we can do it in production environments. While doing it on test devices can give us some initial insights, the measurements in production will provide more reliable data. Depending on how much data we need, measuring in production itself can also, though, have an impact on the performance. So if we add this performance logging, we're adding overhead for our users as well, right? Because we need to store the timestamps, we need to make sure that we have all the data collected, like the necessary data collected. So we should sample the data collection and only execute it on a subset of devices, so we don't impact the overall user experience. In the simplest way, we will just be saving timestamps. So in this example, we're just gonna store the timestamp before the code that we want to measure is triggered, and one after the code path is triggered. And then we just calculate the delta. In this example, we are not using any framework-specific class. We're just getting the timestamp and calculating the delta. So it's quite simple. We're also not doing anything with it. Once we look at real-life scenarios, usually these things become more complex, though. So we would have, for example, multiple steps that are part of the user flows. We would be, for example, saving a message to local database. We would be setting a message up to be sent to servers, and maybe we need to update the view state or any view state as well accordingly. So in this current setup, we would get the overall execution time. That's already a good start, right? Because we know how long it takes to go through the whole flow. But we're not going to get insights into individual sections. So if we see an increase in execution time, we will know it's there, but we don't know where exactly it's coming from. So to get more fine-grained data and information, we can work a bit on the way we measure. We can add points in between to mark specific sections of work. The performance logger that is injected here in the constructor, that's just a random construct. It doesn't really exist. I just needed something for the presentation purpose. So you would have to implement that either in your project or use an existing one, because this would heavily depend on your code base and what you're using. This more fine-grained data will then allow us to check which part of this multi-step flow is a bottleneck, and that can give us insights into how to improve the overall code path, and also how improvements that we already did impacted the code path. All right. So once we have collected these metrics, we need to figure out how to analyze them. So an essential part of performance optimization is to monitor metrics continuously to make sure we catch bottleneck regressions early and we can fix them. So what we end up doing is we will be looking for trends and patterns in the data. We can identify outliers, anomalies, and compare metrics across different scenarios. So it could be, for example, certain device types or network conditions that have quite a strong impact on our overall performance. And we don't want our users to be stuck in a certain flow due to, let's say, low connectivity, or we don't want specific device types, I don't know, foldables, flippables, to have specific issues that other users don't have. So we can use statistical methods. We can summarize, we can visualize the data, and we can turn it into graphs. We can set up thresholds, we can set up alerts to get notifications for regressions. And while we are doing that, when we analyze those metrics, we would be looking for bottlenecks and insights into the critical user paths in the beginning. So if we look at the data, a high average execution time may indicate a bottleneck in the code. So we might be thinking, can we make it faster by optimizing? Can we move it to an async operation? Can we break it into smaller parts and schedule the long-standing operations at some point later? Is it actually needed right now or not? If we look at the standard deviation, this could indicate a variability in execution time. So these will be harder to optimize because there's, let's say, some sort of like flakiness in there, right? So we need to dive in deeper to understand the variability, and we need to add more fine-grained monitoring. So in the end, we are looking for correlations between these metrics, such as execution time and CPU usage, to identify potential causes of bottlenecks. The performance metrics will most often also impact product metrics. So while you're analyzing and reading these metrics, make sure to also focus on your product metrics. Because like what we talked about earlier, right? If the app is faster, people are more likely to convert in your critical flows. So that's important as well. The easiest catch would be a high crash rate is going to impact all of your product metrics. That's the reliability of your app, right? Because people can't use the app at all in that case. Another one would be a high execution time will reduce the number of actions the user may perform. So if it takes 10 seconds to execute the action, the user is just limited in general and can't perform it, let's say, twice within 10 seconds, right? So there's a direct correlation between performance and product metrics as well. So if we look at more large-scale or global-scale applications, the distribution of metrics will provide valuable insights as well. If we compare the 50th percentile, so the average, and the 95th percentile, we can understand the spread of execution time. So a large gap in this could indicate that there's a bottleneck that affects a small percentage of users, but with significant impact on performance. It could even render parts of the app useless for certain users. If the app is freezing, the users are stuck, or the app is just crashing. So based on that analysis, we can then identify optimization strategies. We can focus on the worst case scenario to ensure that the majority of users has a good user experience and a good performance. And we can optimize for the average case to improve the overall performance. But if we look at the average case, that would be the P50, right? So for like most of the users, we need to be mindful of the techniques we are using. So we can use things like caching, parallelization, lazy loading, deferring to reduce execution time. We can reduce the amount of in-memory data to reduce the memory pressure overall. But we also need to make sure that the application works well in low bandwidth scenarios to make sure it's accessible, right? So we need to also take care of the P95. Okay. So the thing is, if we add too many optimizations for the average user that are likely on higher-end devices, this could have a negative impact on the users that are on the low-end devices, right? Best example would be parallelization with increased active thread counts. So once we have that in place and we thought about how to optimize our code path and our application, we need to validate the effectiveness. And this is where A/B testing and experimentation comes in. So we will need multiple versions of the code we could implement also different kinds of optimizations, and we need to test each version of that with a subset of users. Then we're going to use the statistical methods to ensure that the results are significant, meaning that enough users have been exposed and we have enough data collected. And from that, I go back to what I mentioned earlier. Optimization is going to be an ongoing process. It's going to require continuous monitoring and improvement. So what we can do once we have data flowing in, performance data flowing in, is we can set up a dashboard. We can use alerts. We can use notifications to detect changes. We need to regularly review and analyze those metrics, and we need to continuously iterate on those optimizations as well. So the thing is, our app is always evolving, right? We're always adding new features, new stuff. We have to make sure that doesn't impact the rest of the application. So if we look at a couple of real-life examples, these are like, I drew up like some wireframes to make them very generic, but these examples could be found in a couple of applications. The first example would be parallelization of asset downloads. So just moving from sequential to parallel, the primary effect that we are aiming for is a better utilization of the device capabilities and in the end faster rendering, right? Imagine we have like 6 images to display. If you do it sequentially, you have to wait for all of the connections to be established and download it. If we do it in parallel, it's going to be faster, most likely, in our average case. But this has a secondary effect, which is we have a higher active thread count. So this can lead to increased stress on low-end devices. So applying these optimizations in kind of like a blanket way doesn't really work for some of the users. It's going to work out for the P50, so for the average user, because average user is very likely to have not the super low-end devices, but then we are putting our P95 and the users that don't have these kind of devices under more stress. And we are going to reduce their UX, or it's just going to crash at some point. So we need to put in guardrails into place. In this case, it would be a limited parallelism. Based on the device capabilities, we would use more or less, or none at all, if it's too heavy still. So the next one would be about layout improvements. This was definitely an interesting experiment. So in this case, moving from a grid layout to a linear layout and managing the subviews on our own, it sounds a bit counterintuitive at point, because like you would assume that the grid also works quite well. But there's like a couple of differences, right? So When we are switching to, I have like some images on the next slide, so I'll visualize it a bit more in a second. But just to give some like early insights, the grid has more individual cell items, right? And those are part of the layout. So they need to be created, they need to be bound, they need to be displayed, rendered. And switching to a vertical linear layout, in this case, actually had less views that are slightly more complex though. So the primary effect of this optimization would be an improved scroll performance, but then the secondary effect is that the view inflation time increased due to the increased complexity of the views, right? So guardrails we can put in place here are, we can keep the view hierarchy as flat as possible. We can offload all of the binding to background threads and optimize in other ways as well. Okay, so this is a before image, right? It's a grid with individual cell items. So in the actual example that I was working on some time ago, we had about 8 items per row, depending on the device's screen. So what we noticed was there was a poor scroll performance on low-end devices under certain conditions. So after a bit of experimentation and refactoring, we ended up with a slightly different layout. Kind of looks like this. My drawing skills are not the best, so bear with me on that. We moved away from a grid to a linear layout. So each row is now one item, and through that we are reducing the amount of recycled views, so this was in a recycler view, and each row is now a linear layout, a horizontal one, with a predefined amount of child views. What we saw was the scroll performance improved, and there was a very large reduction in frame drops across our users, especially on low-end devices. So the too long didn't read is it's important to analyze layout hierarchy, of course. But there might also be some unexpected areas that can be improved that when you first look at it, they seem like, okay, yeah, this is already quite good, it's quite flat. So it's good to dive in deep to figure out where those bottlenecks are coming from. These are very dependent on implementation and use case, as most of the micro-optimizations are. In this case, we also made some changes to the data pipeline as well. So batching them into chunks of data before sending them to the UI, that was kind of necessary for the new representation. And this also reduced the overall work on the main thread and then resulted in an increase in usage for this feature. So that was quite nice and very surprising. If we look at another example, I think it's a bit underrated, but it's quite a good one. It's view stubs. They are used to extract views out of layouts, right? So the view stub is going to be an empty view until they are inflated on demand in the UI. So as an example, we often want to show a separate experience to new users. So to either educate them, to show them how specific parts of the app work, and how to use features. And since these experiences are conditional, making sure we don't include them in our layout by default is going to improve the performance. So if we look at an example, this is Android views, not compose, so I've shortened the syntax a little bit, or quite a bit, to make it fit on the slide. In the example here, we have a bunch of text views, a button, 2 recycler views, and a linear layout. The linear layout on the bottom contains the new user experience. It's a few images, some text, also a button, and this will only be shown for the first time when you go into this feature, right? So the first time you use the feature, or whatever it is, you're going to see that. And including the linear layout like this, it's always going to be part of the view hierarchy, even if we set the visibility to gone, which makes sure it won't be part of the measuring cycle, but it's still going to be part of the view hierarchy. So if we replace this with the view stub, the layout looks also a lot cleaner actually. And the view stub is going to be inflated on demand whenever we notice that a user is using the feature. So this has a couple of advantages, but it also comes with disadvantages. So since they are inflated during runtime on demand, so for example, when the user clicks on a button or performs a gesture, in a specific code path, it would be a conditional experience. This, So this means that we need to do the inflation in runtime, right? And that can also have an impact, a negative impact on the user experience. It depends on the complexity of the view again, right? So Usually, I think people are more used to having everything rendered in the beginning and then things just disappear and appear. But with the view stubs, they will be inflated and rendered in runtime. So in this example, when I extracted the user experience into a view stub in like a similar setup, I've noticed a reduction in the initial inflation time of around 50%. And 50% is quite a lot. So getting these improvements in high volume surfaces that most users are going to touch and are aware of, it will bring a lot of benefits. Like it's going to make the app quite a lot faster, especially on the low-end devices. Yeah, so especially low-end devices will often struggle with the inflation time of complex views. So this goes kind of hand in hand with other optimizations, like just optimizing the view hierarchy itself. But at some point, we have to do as much as we can to make it as smooth as possible. So this is another example. It's a bit more hidden, but in our apps, we sometimes use application context, right? It's kind of like a global state object of the application. And it can give us access to system services or, for example, cache directories. So if the application context is used in too many places, we can actually end up with random locks. This can also happen on the main thread, depending on how the code is structured. So if we access the application context on background threads and the main thread, there might be some surprises in there that create ANRs. So if we take a closer look at application context, we can see that a lot of these functions are synchronized. They're using an msync lock when accessing, for example, cache directories or file directories. And it makes sense, right? This is done to ensure that the files object, the file object is initialized and that it isn't done like multiple times. So that kind of makes sense. Each of the calls is going to use the same lock even after it's initialized, though. So here's an overview of variables that are sharing the same lock. For example, if we are accessing mcache directory and mdatabase directory at the same time from multiple threads, we might end up locking our threads for a short period of time. So this is especially impactful if we are accessing on the background thread and on the main thread at the same time, because we might want to load something on the UI, but we want to store something in a cache directory on a background thread. So this can lead to super random ANRs that are very hard to debug, and it takes a lot of time to find this and to fix it if you don't know where to look. So it makes sense to be a bit cautious about accessing things. I think that's a general statement in multi-threaded environments. But even things that kind of feel safe can still not be that safe in some cases. So, for example, in this application context scenario, it might make sense if you're using it in a lot of places to have a caching layer for things like the file objects that points toward like the cache directories or other pieces to avoid triggering this synchronization cycle too many times. Now that we looked at a few cases, let's take a step back, look at some best practices. So, in general, it's good to focus on the most critical code paths and bottlenecks. We need to use metrics, we need to use profiling tools, we need to just spend a lot of time reading and understanding everything we are doing. We need to implement optimizations incrementally and measure their impact. And also we have to consider the trade-offs between optimization and maintainability. So it's important to continuously monitor and refine these optimizations over time as our code base also evolves. In conclusion, the micro-optimizations can have a significant impact on performance and efficiency of all applications, but the larger your app is, the more you're going to notice this. So by understanding how to measure and analyze metrics, developers, software engineers can identify opportunities for optimization. And by applying best practices and optimization strategies, we can improve the performance, the efficiency, and the user experience. And continuously monitoring and refining these are key to ensure that these optimizations remain effective over time. That's all I got. Thank you for joining. Thank you for listening. I think we have some time for questions, and otherwise I'll also be around if anyone has any questions about this stuff or just life in general. I don't know. We can talk.
Hi, thank you for the presentation. It was very interesting. I have a question about the balance between optimizing the app and adding new feature. How do you think the proportion of those two, for example, if we think about agile development, if you have sprints of 2 weeks, for example, and objective for each quarter, what do you think the proportion of each part, adding new feature and optimizing the existing features in the development cycle?
That's a very hard question.
Yeah.
I think it depends a lot on like the company culture and like what are like the timelines, right? If there's like a specific deadline from the product side, or like there's like outside things that also impact it, then it's good to shift the focus more on delivering rather than optimizing. But it's also good to just allocate some time with your team or with your engineering team for this. So in general, I think it's a good practice to just also make sure that these things are visible within the company and that there's a certain like reward in a way, right? That there's recognition, that it doesn't go unnoticed. Because in like my career, I've seen quite often that like you optimize a lot of stuff, you work on a lot of improvements, but then it kind of just goes unnoticed because like, oh, it's not a new shiny button or anything. It's just 50% faster. But especially in like startup environments, this can get quite lost. So creating like a culture of that, and it could just be like within engineering itself, like if the rest is like too busy or whatever, that just creating like a culture of like bringing visibility, acknowledging things, and like in the end like kind of like a rewarding system, right? Like celebrating these wins. I think that is gonna increase like the intrinsic motivation as well to keep working on that. And then together in that, you still need to find time for it, right? So you need to still figure out with your team, hey, can we maybe allocate, let's say, 10% of a sprint, 20% of a sprint, or you have like every cycle you have one sprint that is fully dedicated to these kind of things, but that heavily depends on like your setup and like the external timelines, right?
Yeah, okay. I think it's the answer that, that I hoped for. Okay, thank you.
Hi, thank you for your presentation. I was wondering, you've shown us the layout. This is an example, and it's already, at least for me, I struggle with different size of screens. But what about, very specific attributes we can't use in certain versions of Android to conserve the maintainability for lower versions? Do you do different layout, just like for size of screens, or do you try to keep it as simple as possible?
Yeah, that's a good point as well. I think it always heavily also depends on like the use case, right? So it's very use case specific. What I try to do in my day-to-day life is I try to keep things as simple as possible. So because it just reduces complexity in like all of the places. And you can use like different layouts for different versions. If there's a need, like if you, I think it also can make things a bit harder though, because I mean, if we think about the XML world, then it's kind of like hidden because it's done like by the system, by the context, like in the whole like inflation time and like the whole like even compilation time at some point. So in the code, it's probably easier to understand and to maintain if you just have like an if-else condition. But yeah, it depends a lot on the situation. So in me personally, I don't do that much. I would rather do it on the code side. And for example, if you if you have a feature that you know it doesn't work on, let's say, Android 21, then you can encapsulate that in like a static function somewhere and see, can I use this feature? Yes, no, because there might be cases where you identify later on that it doesn't work on Android 21 and it doesn't work on Samsung S22 if it was like with this 8 conditions. So you have more flexibility in those cases as well. Like in the end, there's like, I don't even know how many, like 100,000 Android devices at this point. And this whole matrix would get very complicated at some point. Yeah.
Yeah, okay, thank you. I could use also Google Pay example or something like this. But I was wondering also in terms of time of compilation, do you try to use as less layout as possible for optimization? Or
For the compilation, like to keep the XMLs in that case
yeah,
smaller?
to keep the performance.
I think like the build time and compilation is also an important part, especially if the team grows. But in some cases, like it's more important to keep an eye on the user, because in the end, like there's maybe like a couple of us like working on those files and like compiling that piece of code, maybe a couple of times a day. But the user will always need to use it, right? So me personally, I focus more on like the user experience, the dev experience. There's like different levers that will give you like more things like remote caching of modules and these kind of things. So I think that would be interesting to see as like a micro optimization of the compilation. But I haven't been diving into that part.
Okay, thank you.
Hi. Hi. Thank you for the talk. I had a question about the cycle of your checking the function execution times, for example, then optimizing it, and then again monitoring how did it change. So how, if you actually want to check all of this in production code, then how long does it take you to first, collect this data and then do it and then verify it? And also the second question, kind of related, is do you do some cleanup afterwards, or do you end up eventually with the code where you are logging execution time of like every function in the class,
Yeah, so getting this data, depending on which part of the app you're working on, right, can also take a long time. So it's definitely a process that that needs some patience. If you work on like a niche part of the app, then you won't have that many users going through it. But you still want the data to be statistically significant, right? So you still need a specific amount of data for that. So it can take a while. Yeah, it can take a couple of weeks, it can take a month, it can take 2 months. So it's more of a long-term game. Not really a game, but it needs some time, for sure. So these kind of things, you can't really rush them, because you need the data. You need to know like what is the impact of this optimization. And the cleanup part is definitely also very important. Especially if you're optimizing things like layouts, you would end up with like 2 XML files, worst case, or like 2 different implementations of the layout. And if you have like multiple teams that work on the same layout, for example, they will always need to work for their new features on like 2 files as well. So keeping the code clean is part of the whole cycle. It needs to be done. As soon as you have like significant or like reliable data for whatever you're measuring. And that also comes into what I mentioned earlier, right? Like the performance logging itself is also going to be overhead. So it will also add overhead because you have to like, even if it's just in a map or in an array, you need to store the timestamps somewhere. So you have more objects allocated, you have more memory pressure. So things are gonna also regress, not noticeably. I mean, depends on the implementation of the logging framework, but there's overhead as well. So you should definitely only like measure the parts that you really need to know about. Like the parts that you need to know work perfectly, or while you're working on an act of optimization, for example.
Do you have any cleanup process afterwards? Or do you keep it there?
Yeah, but it's just a manual process, like just deleting the code, like just going like which of these, like if it's just an if-else condition, right, and then it calls a different function, then I would just delete the path that is no longer used. Like the winner stays and the loser is deleted in the end. Yeah. So no traces are left behind.
Thank you.
All right. Thanks everyone again.